So, as explained in the previous video, our little Z80 CPU only has 16-bit address lines, and that means the maximum memory it can address is 64K. In this video, let's take a look at how memory banking on the 128K Spectrum and the Spectrum Next works, allowing these machines to break through the 64K barrier. This video is mostly aimed at people trying to program the Spectrum, but how and why this works is sufficiently technical that I hope it's interesting to more than the 5 people out there who seem to be actually programming like this. In fact, let me know in the comments if you intend on using this to write code on the Spectrum in C, or whether you're just like watching it out of amusement. I'm quite interested in what people do with this stuff. This video is pretty technical, so strap on, sit tight, here we go. Let's look at various Spectrums. Some people have vast numbers of Commodore machines, I have Sinclairs. So here's a Spectrum Plus 3. It's got a whole 128K of RAM. At the time, this was amazing. This one is mine from when I was a kid. It doesn't work. I think it's got faulty RAM or something. Here's a Spectrum 48K. It's got 48K of RAM. Well, this one is a Spectrum Plus, but it's the same kind of thing, you know, it's like putting lipstick on a pig. It's the same motherboard, they just made a less nasty case. Let's go even further back. This is a ZX81. It's the Spectrum's predecessor. It has a fantastic 1K of RAM, and it was widely regarded as pretty awful. I mean, the screen blanked when you pressed the keys because the CPU did everything. Yes, I know you might have fantastic memories of this thing, but compared to this, that doesn't compare. But what do all these machines have in common? Why am I making such a big deal about this poor little device? Look at it, it's harmless. Where is this ramble even going? Let's find out. Well, it's all to do with this little chip here. This is the Z80 CPU. This one is from my RC 2014 computer I built the other year. Yeah, I told you I've got a thing about Z80 based machines. I don't know why, I guess it's what you grow up with, you get attached to. So this CPU is the main thing. It's made by Zilog. You can see it's got a set of address lines and a set of data lines coming off it. And more importantly, there's 16 address lines and 8 data lines. The 8 data lines are what make this an 8-bit CPU. Inside the CPU, those 8 lines go to the registers, each of which are 8 bits wide. 8 bits in binary gives us a value from 0 to 255. The address lines form part of the system bus. This is a RAM board from my RC 2014. You can see the address lines on it. Since there's 16 address lines, the CPU can address up to 65,536 different locations. Each of those locations can store a single 8-bit number. That gives our CPU 64K of addressable memory. And that's it. But 64K is loads, surely. Surely we don't need much more. Well, it's not enough. Or really, by the time these machines had been developed, technology had moved on and memory was much cheaper, and how much RAM you had was actually a selling point. So on the 128K Spectrums, how does the 128K of RAM and 32 or whatever of ROM fit inside that 64K of addressable memory the Z80 can see? Like, that doesn't fit, does it? It's too big. Well, it's magic. No, really, this stuff is actually proper magic, and it's kind of the point of the video. Just how did Sinclair manage to make this machine access 128K of RAM? All the magic is inside this chip here, which on my Plus 3 is a gate array. You know the ULA on the Spectrum? If I just get one of those. There it is, that chip there. That's an all-purpose chip that makes this computer a Spectrum. The gate array on the Plus 3 is that with extra bits added. And the gate array on the Plus 3 contains all the logic that was in the ULA, plus a bunch of other logic for bank switching, and so on. Also defined using logic equations. It's the same as a bunch of hardware logic gates, just in one cost-reduced package. It's sort of the great-grandfather of the FPGA in the Next, except the FPGA on the Next is that, plus the CPU and everything else to create the whole machine described using logic equations. In fact, the only part of the Next that is not inside the FPGA is the RAM. I know you can describe any logic circuit using an FPGA, but is the reverse true? Can you describe every FPGA circuit using real hardware? You know, is that a thing? I don't actually know. I know that with the appropriate tools, you can reprogram this hardware to be something different. It's not inherently a Spectrum computer. This could be something else, and there are other cores for it. But that's a rabbit hole in a rabbit hole to go down another time. We're not breaking through the fourth wall of FPGA design today. Maybe in the future though. I quite like this low-level hardware stuff. It's quite fascinating. I just used magic words then. Bank switching. So what's that? Well, it's a clever tactic that's still used kind of to this day as a mechanism to decide what areas of memory the CPU can access at any one time. The idea is to partition memory up into banks of a certain size, and then let the programmer attach those banks to part of the CPU's address space when it's needed. It's a bit of a mixture between physical hardware design and abstract program logic. On the original Spectrums, this was done using 16K banks. The original 128K Spectrum and the Grey Plus 2 have a particular memory layout that allows us to access any of the 128K of RAM through the top 16K of address space. Also, you can page in and out parts of the extra ROMs as you need them. And you do this, it's not that difficult, by writing to IO port 7 FFD, and you set the first 3 bits to the value of the bank that you want. On the Spectrum Plus 3, it's a bit different. They updated the design to allow a bit more flexibility so CPM could be run. You could write to ports 1 FFD and 7 FFD to control what is banked in and out of the CPU's address space. The Next can do all that plus its own much more flexible memory paging, because on the Next you use 8K blocks and you can switch in and out of any 8K area of the address space. The specifics of this we'll come to shortly. The reasons for all these highly specific banking systems on the original Spectrums can be explained by having a look at the schematic, which is pretty interesting. So here's the one from the Plus 3. From the circuit diagram, we can see the machine is physically wired up to allow 2 of the memory chips to be directly accessed by the CPU, along with the ROM chips. Selecting which parts of this is handled by the gate array somehow. The gate array is a bit of a magic black box. The 2 other memory chips though are only attached to the gate array. They don't connect to the CPU, so clearly the gate array controls how they get accessed. This results in a new memory banking layout with 4 modes. I bet being a Plus 3 programmer was exciting, having to carefully plan which parts of RAM contained what. I bet that's why there wasn't much Plus 3 specific software. Programmers don't like excitement. It's customary for machines to have what's called a memory map. It's a diagram of where things are in RAM. Having one ensures you don't go stomping all over important structures in RAM when you're trying to write your own code. So this is a Spectrum 128K memory map. And here's the Plus 3 one. What you can see is RAM is arranged into banks, and part of the CPU's address space is able to be connected to one of the banks at a time. If you look in the Next manual, you'll see a nice little memory map explaining where things go in that machine's RAM. And if you look at all these things filling up RAM, loaded into specific parts, it feels a bit complicated, as if somehow we have to take this into account and neatly thread our own little program amongst the space, being careful not to stand on all of this data that's already there. Well, the trick on the Next is what you do is you take the memory map and you stick it in the bin. Just get rid of it. It doesn't apply to us, none of it. Yeah, I know that there's a bit telling us not to bank in and out RAM as we please because it'll upset the operating system and BASIC. Well, where we're going, we don't need the operating system or BASIC. Who cares if we stamp all over the BASIC interpreter's system variables? We're never loading BASIC back up ever again without rebooting the machine. We have full control of the machine, and once our program loads, we're not going out of it. The only way out is to reboot. And this is a fundamental thing to understand about 8-bit machines. Once you escape BASIC, I mean we're not even going into BASIC, you get the machine all to yourself. From then, there are no rules but the ones we make ourselves. So if we have full control over the machine, what guidelines exist to help us choose where to put things in RAM? What rules do we make up? What are the defaults? And where does our code get loaded? And if we start playing with bank switching, what's stopping us from crashing the machine? To understand the machine properly, first let's have a little diversion and work out what happens when code is compiled. Have patience, because the answers to those previous questions are coming. We're using Z88DK for this, because we're writing in C. Turns out that this is like writing code on nightmare difficulty, with permadeath switched on. Just let me explain. You see, easy mode is us doing it in pure assembly, if you're wondering. A lot of what I'm trying to describe is very common day one assembly programming concepts. However, using Z88DK hides and implies some of this stuff, and working out how to manually alter it takes a bit of digging around in documentation. Remember, assembly language is about as pure as you can get when talking to a CPU. C, by its own nature, abstracts away some of that direct nature, so we have to figure out how to directly manipulate what we're trying to do. So in order to use banking, we need to figure out what the next is doing with its RAM and where our code even goes when it loads, because we don't want to accidentally start moving banks around and move our code out of RAM. So from a bit of experimentation and a bit of thinking and asking some very specific questions, I found out Z88DK assembles your code to run from location 8000 hex, which is the second 32K of the address space. This location of where code goes is known as its origin, and it can be adjusted by defining a pragma in Z88DK's configuration. If you didn't know, a pragma is an instruction to the compiler to tell it specific configuration options. They're a bit like switches on the command line, but they're usually more fundamental to the code being generated. Another thing we need to worry about is a stack pointer. The stack is used to hold the return address and function parameters between function calls, and the CPU doesn't work without one. We can move the stack pointer by setting another pragma. Another part of the CPU's functionality that needs considering are its interrupts. Now we can either disable them and pretend they don't exist, which might be a good idea, or we have to configure them somehow using what's called an interrupt vector table. This is a future video, so I'm not going to go into it much here. But setting up interrupts is done by us writing code, and we need to reserve some RAM for something called the interrupt vector table. But it's not like setting a stack pointer or anything. We don't specifically do anything. We just more remember where we've chosen to put it and make sure we don't write anything in there by mistake. And this is like a main concept. We're 100% in charge of the machine. It's up to us to decide where things go in RAM. And some of the things are not configured anywhere. It's just us making a decision and sticking to it. Now this sounds great, but it doesn't tell us anything about where these things should go in the address space, nor does it explain anything about the extra RAM in the next. And that's kind of the point, so I should probably get on with this. However, those of you that are still awake might have figured out where this is going. If we know where our code is being loaded, and we have the ability to move the memory around, the answer to most of our questions above are it doesn't really matter where any of this stuff goes. So the next comes with a Z80 CPU. It's got 64K of address space, and it starts at location 0 and it goes up to location FFFF. It also contains at least 1 megabyte of RAM and can optionally have another to make a total of 2 meg. As an aside, we don't get the whole of the first meg to play in. 256K of it is reserved for the next internal workings at a level below what we can affect with our code. I kind of lied when I said we have 100% total control of the machine. What I really meant is we have total 100% control of the simulated spectrum running on the FPGA. We can't affect the way the FPGA works by writing this code. That is below our level of influence. And that's partly where the missing 256K goes to. If you're curious, it's where all the system ROMs get stored. Just mentioning that because some of you have spotted the number of available banks and the amount of RAM listed in the manual doesn't appear to add up. So to stop this getting too abstract and too weird, let's look at something simpler. Let's look at the original Spectrum Plus 3. It helps explain the concept a bit. You see, that was organised into 16K blocks, and they were very specific in where they could be put. And by using banking, it was possible to switch out the upper 16K of RAM from address C1000. Imagine the larger 128K of RAM is chopped up into 16K banks, and you can swap in and out the banks as you want, but you can only have one bank in use at any one time. The next takes this to the next level, cheesy pun. It uses 8K pages instead of 16K ones. It does mention in the manual that there are 16K pages, but use 8K memory mapping, works much better. And since it has up to 1792K of RAM, that gives us access to 223 8K pages that we can play with. Something that's worth noting is that the next wiki shows a certain layout that is in the RAM at the start when the operating system boots. We need to bear this in mind as it gives us a bit of information about which specific memory banks are in use to start with. Also, there's the curious design that one of the banks is always available to the ULA, even when it's not banked in. But what we need to remember is that our code is loaded into some memory banks when it starts up, and we don't have control over that, or at least not at the moment. I think you can make Z88DK set the RAM up for you, but we'll just go with what the machine is when it's turned on. So let's actually figure out some kind of sensible memory map for our own code. So we've got the 64K address space, from 0 all the way up to FF. And if we cut it into 8K pieces, they can be numbered like this from 0 to 7. So let's put the ROMs and layer 2 in the bottom two banks, which is 0 and 1. Now I just said the code origin is 8000 hex, and that is bank 4. And we need to put the stack pointer somewhere sensible. It starts out at the top of RAM, somewhere up high about FF something or other. But if we did that, we can't really use any banking, as we might accidentally bank out the stack. Then the machine would crash. So we can move the stack, and let's put it in the top of bank 5. Now we'll need to somehow be careful, to the best of our ability, to avoid our code growing into the stack if we write too much, or the stack growing down into our code if we use too many function calls or something. Now this layout leaves us with some nice gaps. We've got banks 2 and 3 that are now unused, and so are banks 6 and 7. So we've got about 32K of address space to play around with. Now what I've done is chosen to use banks 2 and 3 as scratch memory for things like loading layer 2 images before they're copied to the screen using DMA, and DMA is a future video, so be sure to subscribe so you can watch that when it turns up. And if you want to see how layer 2 works, I've made a video on that as well, which you can go and watch after this one. I can then use banks 6 and 7 as general RAM for whatever I want. I could put code in it, I could put data in it. It's up to me what goes in there. Now it looks a bit messy with all these random holes in memory. It'd surely make more sense for the code to be in bank 0 and 1, layer 2 to be in bank 2 and 3, and then the upper 32K to be entirely free. And yeah, that would indeed be more tidy, but I couldn't make it work for reasons I fully don't understand, and I kind of lost interest in trying to work it out. What I've got here works, and that's actually good enough. Also, if I keep layer 2 in the first two banks, then all the offsets into it map to direct pixel locations, like memory location 0 is screen location 0. Plus, the machine itself doesn't actually care, so why do we? We just need a working machine. Right then, now we've fully understood how to organise our RAM, and I did warn you this was an in-depth video. Now let's look at how to actually make use of it. So the one trick with this is to realise memory addresses from the CPU's point of view, they all stay the same. It has no idea memory banking is happening. The next has what we call MMUs, which stands for Memory Management Units, and they handle the actual bank switching. It's not any kind of segment and offset system from the PC or whatever. You know, you're not asking the machine for bank 6 location FF. Instead, you're telling the machine to put bank 6 into MMU2, and then you write to memory location starting at 4000 hex, because that's what MMU2 is mapped to. If you then put bank 16 into MMU2, you still write to location 4000 hex, but you'll then only have bank 16 in that location. It's quite easy to control this. I found some code online, and here it is. It's really short. All it's really doing is writing to a register. It is also trying to be nice and do a bit of housekeeping by returning to you the memory bank that was originally mapped so you can switch it back afterwards. And the general way you're supposed to use this is to bank switch in memory that you need, then you use it, then you put back the bank that you switched out. But you totally don't have to. That just depends on your own code and what is happening next. You know, if you're writing code that gets called repeatedly, maybe you don't want to switch any banks at all. There's no requirement to put the memory back, because you're in control of the machine. And if you're writing a game, or something that has no intention of ever returning to the operating system, you don't have to put the memory back to how it was before you started. Also, watch out for pointers, especially global ones, because if you assume they're always valid, but then you switch out the memory that they're pointing to, they're no longer valid. So don't make global pointers that point to data in a bank you might switch out, because then it's not global. Bank switching happens outside the CPU's control. It has no idea what's happening, and the compiler has no way of detecting this either. It's 100% up to us as programmers to manage this. Now, accessing the memory directly isn't something you normally do in C. In fact, there's Stack Overflow and whatever things telling you not to do this and that you should always use the memory allocator. Well, there is some actual way of doing this, and here it is on the screen. So what use is all this then? Well, who cares? Isn't it fun being in total control of the machine? You know, there's no operating system in the way, and you didn't stick those 2 extra RAM chips in your necks for them to be used, did you? You just saw the empty slots, found some on eBay, and shoved them in so the number at the start was bigger. Well, okay, let's have a slightly more sensible answer. You could try some of these ideas, I guess. You could write a game. You could make each level's data be stored in structures and fill up memory banks with them. Leave your game code in a bank you never switch out. Then you could actually make a Spectrum game that has more than 4 levels and is an actual true mega game. Now we've got 28 MHz Spectrum with over 1 MB of RAM and 256 colours. We can do more. You know, you could have fancy pictures in your game and preload them all into RAM at the start so the game feels better when it's playing. Although with an SD card, loading is pretty instant, so it's not like you're asking the user to press play on a tape just to load the background for your next level. But you can now have nice backgrounds in your game and switch between them, instead of having yet another Spectrum game where the background is black for 90% of the time. The main use of memory banking though is the one I'm not mentioning specifically in this video, because I've not yet quite figured this bit out. It's where you can run code from different banks. You can load in a bank that does a certain piece of code, then unload it and load another piece in. So you can have code that is more than 16 or 32K in size. Another thing I need to work out is a sound. Well, with lots of RAM and a machine that actually has decent sound, you can bank in music data from the SD card, make a decent sounding theme tune, or have sound effects in your game. And you could combine that with things I'll do in future videos, where you have like interrupts that drive all this in the background, and DMA to quickly load the data in. So there we go. That was a rather intense and deep look into the next memory. Come back next time when we look at the super bizarre world of interrupts, because they're really strange. You thought memory mapping was odd. Wait until you see the craziness of how Sinclair implemented interrupts in their usual cost-reduced and simplistic way. It's really, really clever. The way it works is like pure genius, but it's also very, very strange. It's like proper hardware designer level thinking. So if you're still watching, well done for making it to the end. Do me a favour, if you haven't already, press the subscribe button and maybe share this video somewhere if you think it deserves it. Tell the almighty algorithm gods that this video was worth watching. And until next time, see you later.